Hi everyone, in today's class we are going to apply everything we have learned in this mechanical energy module. Recall that Amanda was observing Jota in one of the basketball training sessions in Module 1.5. On this occasion, with Amanda's help, we draw the trajectory of the ball, remembering that we did it from the position vector, calculating the three components x and z for each of the time instants. We represented these components graphically and obtained the trajectory. We also calculated the instantaneous speed, the velocity modulus. We did this by deriving the position vector with respect to time. Thus we obtained the velocity vector, then we calculated its modulus and obtained the different values for each of the time instants. Now Amanda asks us to calculate as a function of time the kinetic energy of the ball, the potential energy, the mechanical energy, and the velocity with which the ball arrives at the basket. She reminds us of two important facts, that the mass of the ball is 600 grams and that the acceleration of gravity is the familiar 9.8 meters per second squared. Let's first calculate the kinetic energy. We already know that it is a mean of the mass times the velocity squared. The mass is a given. The mass of the ball is 0.6 kilograms and the velocity is calculated as we have seen in Module 1.5. With these values, we have been able to calculate the kinetic energy in each of the time instants. In the graph, we remember the trajectory in green dashed line, and with gray continuous line, we have represented the values of the kinetic energy. As the kinetic energy is proportional to the velocity, we can see how the maximum value of the kinetic energy is given for the initial instant. Jota threw the ball at 8.48 meters per second, and this speed is the maximum speed that the ball reaches along the trajectory. The minimum value of the kinetic energy is given at the instant of time when the ball reaches its maximum height. Since at that moment the ball is going the slowest at 5.44 meters per second. Now let's calculate the potential energy. We know that the potential energy is equal to mgz plus the potential energy in the reference we take. In this case, I'm going to take as the origin of potential energy z equal to 0, the ground. So in this case, I will use this expression, potential energy equals mgz, to do the calculations. M and g are data, 0.6 kilograms and 9.8 meters per second squared respectively. And z we have calculated as we have seen before in Module 1.5. With these values, we obtain the potential energy for the different instants of time. In the graph, we remember the trajectory in dashed line, and then we have represented the potential energy in continuous blue line. As the potential energy is directly proportional to z, we can observe that when the height of the ball increases, the potential energy increases, and when the ball loses height, the potential energy decreases. Let us now solve section 3, the mechanical energy of the ball, as the sum of the potential energy and the kinetic energy that we have just calculated. The table shows the values calculated in these last two sections and the sum. We can observe how the mechanical energy in all the instants of time gives us the same value, 33.3 joules. We have represented in the graph the potential energy in blue, the kinetic energy in gray, and the mechanical energy that we can observe that it is a straight line, which is constant. Therefore, the theorem of conservation of mechanical energy is fulfilled, because in this case the only force that works is the weight. It is a conservative force. Finally, we are going to calculate the speed with which the ball arrives to the basket. In Module 1, we already did it. We already did that calculation. As we said before, we derived the position vector with respect to time. We obtained the velocity vector. Then we calculated the module for each of the time instants. The instant in which the ball arrived at the basket was this one. Therefore, the velocity, the result, was 7.17 meters per second. This time we will obtain the same result by applying the theorem of conservation of mechanical energy. The instant of interest is the moment when the ball reaches the basket. We are going to call it point C. At this point C, the data are the mass of the ball, the 0.6 kilograms, and the height of the ball that coincides with the height of the basket, about 3 meters. With these data, we can calculate the potential energy of the ball at this point, which is 17.84 joules, as we have just calculated. Since the theorem of conservation of mechanical energy must be fulfilled, and at this point the total energy must be 33.3 joules, as in any other instant of time, this means that the kinetic energy must be 15.4 joules. As the expression of the kinetic energy, we know that it is a half of the mass times the velocity at that instant of time squared. From there we can clear the value of the velocity of the ball when it arrives at the basket. And it coincides with the one we got in Module 1, 7.17 meters per second. And that's all. We have reviewed the concepts of potential energy, kinetic energy, mechanical energy, and we have applied the theorem of conservation of mechanical energy in a case in which only the weight force was acting, which is a conservative force. Well, here ends the course of mechanics, in which we have seen the requirements in this subject so that you do not have any problem to study any engineering. You have this course open until the 25th of April. I hope you liked it.